Now let's come to another deviation, which is to have more flow. The cause here shall be mainly due to more flow from feed or that the control valve is in the open position, whether due to mechanical failure or a control loop failure, or because we are now considering changing the valve fail action to fail in the open position if the instrument air was cut. The consequences here shall depend on both liquid and vapor rates. If we are talking about more vapor flow rate, then this shall lead to either the rise of pressure inside the vessel, which can eventually lead to a pressure that is greater than the vessel's design pressure. This will eventually lead to an overpressure scenario, or otherwise it can lead to more gas flow either to the flare or to the gas plant. If we are talking about more liquid entering the vessel, this shall eventually lead to the rise of liquid level and vessel overflow. In addition, more flow would mean that the separator may not do its job well, as the vessel is sized based on specific water and oil flow rates. If it received higher rates, separation won't be that efficient as we are requiring the vessel to act. This can happen in the water compartment or in the oil compartment. In both cases, these can lead to more oil escaping with water, which shall lead to a huge load of wastewater treatment. Or it can lead to water escaping from the weir to the oil compartment, which shall mean off-spec oil and higher load on the desalter package as well. It can also be more vapor entering to the vessel. So, in a real HAZOP, we should address each scenario separately. So, if we have a level rise in the vessel due to high flow, this is commonly checked in the deviation related to the high level. As we see, there is a level control in the water line. This shall adjust the flow during normal operation. But could it be considered as a safeguard? Well, if the failure in the inlet flow was just related to the flow control loop, then the level control loop should ensure that the level is still in an allowable region, which can be considered as a safeguard in this case. However, if the failure was related to a common cause that leads to failure in both loops, such as instrument air failure, for example, and here we see that the fail action of the valve is fail closed, or there is something wrong in the control system itself, or there is some power failure, then in this case we cannot consider the control as a safeguard. Still, we are having other safeguards. For example, we have high-level alarms from instruments. This usually gives the operator 1 minute to respond before the level reaches the high setting, where some action would be taken by the shutdown system, and the size of the vessel would consider 1 minute for the design flow rate. The operators should be trained on what to do in such situations, but we should give them more room to act, especially that the timing can even be less when there is higher flow, which is the case with the deviation we are already talking about in this situation. Now, what about the shutdown action? If the operator didn't respond, then there shall be a high level alarm. But what shall the shutdown action trigger? Could we trigger the shutdown valve in the upstream system? This could be done. However, we should recall that there is another train that is identical to this train. So we are having this line that goes to train B, which has identical vessel with identical controls. So if we stop SDV1 and SDV2, this shall not only stop the flow to our vessel here, but it shall also stop the flow to the other vessel, which shall mean total production loss. And if we added a shutdown valve to stop the flow to the inlet vessel after FV01, this shall also be a source of overpressure, which we were already trying to reduce its frequency. So the shutdown action here is considering that the SDV01 and SDV02 shall close only in case we received high level alarms from both level transmitters in this train and in the other train B. This may not be shown on the P&ID due to congestion, but it should be shown on the cause and effect diagram, which should reflect all shutdown logic. However, the shutdown action shall not protect one vessel from overflow if there is no high level alarm in the other vessel. So, to sum up the safeguards we are having here, we are having three safeguards. We are having level control on the level side. However, it can only be considered as a safeguard in case the failure was local in the inlet flow control loop. We are also having a high level alarm in the vessel on both oil and water sides. However, the operator may not have enough time to respond, and we are having SDV1 and SDV2 that shall stop the flow to both trains A and B in case common failures such as general instrument error or power failures occurred. These safeguards don't seem to be enough. So what shall we do? Let's see in the next video.